Bom dia a todos. Vamos começar a aula de hoje. So today I am going to talk more about algebraic de Rham cohomology. Felipe, está escutando? Deixa eu ver o que está funcionando.
Sim. Tudo certo.
So today I'm going to talk more about algebraic de Rham cohomology. And maybe this citation from Lefschetz, a nice citation, the switch from topology to algebraic geometry, that when I do feel, however, that while we wrote algebraic geometry with capital letters, then while Zariski, Grothendieck, they made it algebraic geometry with algebraic, all written in capital letters. And in this course, we will try to make a balance between topology and purely algebraic. Anyway, okay, so I think you see the presentation. So this is chapter 5 of my lecture notes with Roberto. And today I'm going to talk about this chapter. Anyway, let's start writing. Okay. Okay, let me one second. Okay. So again, X XPN was a smooth projective variety. And so in order to emphasize that it is an algebraic variety, well, for the moment, our complex number, we use this notation. And actually, this notation over something is invented by Grothendieck. I was reading in some interview of somebody related to Grothendieck that once he saw Grothendieck writing, thinking about something, and then just scratching this like this and making a very thick slash while he was thinking. Anyway, it seems that this comes from Grothendieck when you write X variety over something. And okay, then as I said, we introduced algebraic de Rham cohomology, H, M, de Rham, X, C. We defined it as hypercohomology, H, M, the complex of algebraic differential forms. Soon we will back again to explicit description of elements of this guy. And from another side, let's consider X as a C-infinity manifold. The difference with the previous lectures that I will consider X infinity with Zariski topology also. Zariski topology. In the previous lecture, I considered it with usual topology with the small neighborhoods, but this lecture I will consider X infinity with the Zariski topology. And therefore I can consider also the double complex of C infinity differential forms on X infinity. And something that in the previous lecture we saw, that actually today I will write it a little bit more explicit. If you take this hyper cohomology x infinity, and then this guy. Since C infinity differential form, they do not have any cohomologies. Let's say x infinity omega q x infinity is equal to 0. Let's say m is m for m all m bigger than equal to 1. Today we will see that using partition of unity, how we can explicitly check this statement. But something that we observed in the previous lecture, when you're complex, it doesn't have any non-trivial cohomology except in m equal to 0, then this hypercohomology is basically the global section. And when you take the global section, you will land on this classical de Rham cohomology, Hm de Rham x infinity, and this is kernel of anyway, let's read out right in there. So this is global C infinity closed M forms divided by global C infinity exact M form. Okay, and okay, so far so good. So today I want to explain that these two cohomologies, they are basically the same. And of course, the advantage of this cohomology is that we have constructed it by polynomials. But for this cohomology, we are using the category of C infinity function. So whenever you are able to construct something with polynomials, why you would go and start using a bigger set like C infinity functions. So let's explain. So we have this inclusion, this map. So algebraic differential forms, the complex. We have this inclusion inside this C infinity differential form. As I said, now I am using Zariski topology for x infinity also. And again, you mentioned that now you take the hypercohomology. Once you take the hypercohomology of this one, we called it algebraic de Rham cohomology. After taking, I have to, taking hypercohomology. So here we have Hm de Rham x over C. And from the other side, we have the classical de Rham cohomology. So today, even so that theoretically it is already done, that we know this how to say, this map. I will try to write down this map explicitly. Let me call it. Okay, so this will be. I will call it this one A. Okay, in a minute I will name it. Okay, so something also that in the last lecture we learned the concept of quasi-isomorphism. So let's repeat it again, that we have a quasi-isomorphism here. Let's call this one I. I is a quasi-isomorphism. Again, what is the definition of quasi-isomorphism? So locally, this map must induce inclusions, induce isomorphisms in cohomologies when you take the kernel divided by image of the subsequent maps. So remember that now we have here a Zariski topology, and let me first write this. Follows from Atiyah-Hodge theorem. And but let me explain. So if you take a affine open set, so the quasi-isomorphism is a local condition. So this means that I have to restrict myself into let's say affine open Zariski open set. In this case, I will restrict myself to affine open set for U affine open set, affine open set in X. Then what I have to restrict all differential forms here to U, and then prove that I have isomorphism. So I will have what? Maybe just I will write in as in words, algebraic closed, let's say M forms, algebraized exact M forms, of course, where in U, when I take this local cohomology, then I will have this C infinity closed M for the U, C infinity closed M form in U. So this refers to here. And Atiyah-Hodge theorem, what he was saying, Atiyah-Hodge theorem was saying that this map is actually an isomorphism. And this is the definition of quasi-isomorphism here. So locally forming cohomologies here and here, this inclusion will induce an isomorphism. And something that I mentioned, whenever you have a quasi-isomorphism, this implies that, so the induced map HM de Rham X over C, this is an isomorphism. So the moral of the story is that the algebraic theorem cohomology is the same as C infinity cohomology, but of course there are two advantages. Later we will see that we can replace C with any field. Well, for our application field of characteristics 0, and this guy is constructed by polynomials. Okay. Even so that theoretically we know that this is an isomorphism, today I want to emphasize that this is an not existential isomorphism. This is some concrete isomorphism, because something that during the course that we would like to do, for example, we will in Felipe's talk, we saw that there are coproducts defined here. So the idea is that we can transport, since this isomorphism is kind of unique, then we can transport this coproduct here and define algebraic coproduct and so on. So the description of this isomorphism is very important. So I will denote this one by A minus 1, and then A, so, and then I will also describe the inverse of this one, HM de Rham X infinity going to HM de Rham X over C. Okay, so even so, theoretically, I say that we have already done this. We have proved that these are isomorphisms, but I want to write down explicitly these isomorphisms. In my book, I have written in a more just as a text, but I will try now to write down it. As in a diagram, such that it becomes clear. So let's say I write this one A and this one A minus 1 because first I want to write down something, have to describe A. Description of A. Okay, let's go. We have to, in order to this one, we have to remember our double complex that produced the hypercohomology. Well, for this one, just a moment, I have to write down. Okay, let's remember here. Oh, let me. Okay, in any way, before to this chapter, Algebraic de Rham-Cohomology chapter, there is a chapter in a more general shift theoretical context. Well, let me simplify to that notation. So SI, that will be, that's SM. It is omega m x over C, differential M forms. And remember that there was this maybe, okay, SM. I think let's put I here because I. And then there was this SIG. This G was actually the G0, G1, GM. And let's say I fix covering UI. In our context, UI, maybe I for this one, okay, UI0, UI1. Let me see which notation I have used in my. Okay, I think it is much more safer that I put the G notation here. Otherwise, I will make confusion. And then the I is reserved to the check cohomology notation. Then I is I0, I1, I, let's say, actually I. Okay, let's do this. I. So I1, then just a moment, I have to check the notation in my how it was. Just a moment. Otherwise, I will produce different notations and then. What was that? Oh, just a moment. Yeah, okay. So actually, it doesn't matter actually. I put. Sorry for this confusion, but let's just fix this notation. M on the top for M differential M form, G in the bottom. G, and then this will be I0, I1, then IJ. Okay, and then we will take a covering. Such that all the intersection UIGs are affine, because at the end we will use Atiyah-Hodge theorem. Okay, so in order to describe this isomorphism, remember that what we did. We will write the double complex, but I will write the part of the double complex that I will need here. S0M, S0, S1, m minus 1, blah, 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 blah. Then s m 0. There was a differential going from this side, the delta going from this side. So, and this d and delta. And yeah, okay. So in order to describe this, now I want to describe this map. Okay. First of all, this what is this this map? Let's. I want to write down a. Okay. I will take omega in Hm de Rham x C infinity. So this is a C infinity differential form. So what is omega of this one? Omega of this one, in order to write down the omega of this one, omega is given by, so we put it here. This is the collection of, we restrict omega. So let's get the class. So omega is a C infinity form. We restrict omega to each ui. And actually what it is, so let's say, let me write here. So we have this, this is going to be, omega 0. Remember that a general element was of this type, omega m minus 1, omega 0, and in our context, this is 0, this is 0, and then there is this omega 0, then omega 1. Omega 1 is where? It is in m minus 1, 1. And yeah. And then, okay. So the omega is just a restriction of omega to ui's, and this gives an element in the hypercohomology of C-finite differential form. So the idea is that we have to transform it to algebraic differential form. Of course, this is a well-defined element in hypercohomology because its d is 0 and its delta is equal to 0. Delta is equal to 0 because it comes from global. So now we have to, well, actually, I'm making a kind of not, well, the point is that our omega must be algebraic. So actually, this is not really our omega. This is what I want to say, that we have to start from this omega 0 and transform it, and omega 0, 0, 0, 0 here, and transform it to something algebraic. Okay, so what is the process of transformation of this guy to algebraic? Okay, so how it works? Let me write it. So whenever we restrict it to ui, we use Atiyah-Hodge theorem, and whenever we use Atiyah-Hodge theorem, maybe before going let me look my book, because otherwise I will produce different notation. Okay, let me. Just a moment. Atiyah-Hodge. Okay. No, okay. So let me follow the notation in my book. So let's call this one we put a check here. So what it means, check at the end, this omega check that I have, it is in the hypercohomology M of x x infinity. And I want to produce the algebraic. Okay, so let's start. Okay, first I see omega ui, and this is a C infinity form. And by Atiyah, this gives me an element in the de Rham cohomology of the affine variety ui. By Atiyah-Hodge theorem, I know that the de Rham cohomology elements of affine varieties are represented by algebraic forms also. What this means, so this is omega. So let's call this one omega check I. So omega check I is also represented by algebraic form. Maybe something I will also. Oh, sorry. Then let me. I have made the mistake. This upper index, I have to reserve it for differential for omega 0, omega m minus 1. So this is 0. This is actually 1, and this is 0. And let me see. So this here we have omega m. And omega m is consist of omega I check. Maybe again putting check everywhere. Anyway, let's start. So I will put this OM on top of my notation omega to remember that it is a differential M form. And then, as I said, this lower index will be for check cohomology. Okay, omega mi is now check I is omega m I minus d eta check m minus 1 I. Okay, so what is this? So first of all, this is C infinity form. This induces an element in algebraic de Rham cohomology of affine variety ui, and this affine any element of this de Rham cohomology is represented by algebraic form. So this means that there is some algebraic form, M form, such that this and this they represent the same de Rham cohomology element. So this means that they are different, must be exact. So that's why we're here. So this is C infinity. Our C infinity notation I will put check, and for algebraic notation I will put I will not put check, algebraic. Algebraic, and then this is C infinity. So this is done. So the idea is that I want to replace this omega m with this. So let's try to do this. So let's try to do the here. Let me see. Okay. So maybe I write it again here. Omega m. No, I have omega m. My omega m. My omega m is d exact. But the point is that when I put let me touch the omega I m check. So we apply this delta here. When we apply delta here, when so let's apply this one here. So delta omega, let's say omega j m minus omega I m is it's equal to. So since this comes from global, this omega I m check and omega j m check are the same, but the point is that this will be exact. omega jm minus 1 minus omega I m minus 1, check. And maybe again, and it so now algebraic objects is a differential of some infinity form. Again, remember that by Atiyah-Hodge theorem, if this means that this guy must be 0 in the algebraic context also, what this means that at the end of the day, this will imply that omega jm minus omega im must be exact in the algebraic category also. This means that there will be omega ij here, algebraic m minus 1 form. And so twice we use in two parts Atiyah-Hodge theorem for this omega m. So first omega m check has algebraic representative, then we make a delta. And when we make delta, then omega gm minus omega im is exact, but in the C infinity category. But by Atiyah-Hodge theorem, it must be exact in the algebraic category also. So the omega gm omega I must be the omega ij. So what this means that at the end, if I take let's say I put, this is omega m. Now I define omega m minus 1, the collection of these guys, omega m minus 1 ij's. At the end, what I did, I discovered this omega m minus 1, and the moral of the story is that now I can replace my original C infinity thing with this let me say okay, so let's try to do further. What else we can do? Let's try to analyze this one. So we have to still further analyze. When we take the d capital of this one in the double complex, we will get 0 here. But it might happen that delta of this one is not 0. So let's see what is the delta of this this omega m minus 1 j. Okay, so so again, okay. I have to combine. I know I want to combine these two equations. So differential of omega j, so the left hand side is the same, check m minus 1, check m minus 1 I minus omega ig m minus 1 is equal to 0. I'm just writing this together, this one, because the left hand side is the same. Again, for the third time Atiyah-Hodge, it means that again Atiyah-Hodge, what it means, omega j check m minus 1 minus m minus 1 I minus omega ij m minus 1 is represented by differential of this guy in a u. This is we are Atiyah-Hodge in ui intersected with uj. So what this means, that this is let me say okay, so this is minus some algebraic is d something. Yeah, okay. And the point is that here we have, maybe I write explicitly. Okay, so let's say minus some, let's say, omega I j m minus 1 algebraic tilt is d of some c infinity form. I think I will not need, maybe I write it. Let's say omega eta I j m minus 2 check. And the point is that since I have well, this omega ij tilt can be absorbed with this one because I didn't have any canonical way of choosing omega ij. But what I am said, considering absorb this one getting absorbed with this one, at the end I can write in this way: omega j check m minus 1 minus omega a check m minus 1 is exact. Minus omega I aj m minus 1. So I will replace omega ij m minus 1 with this with the sum with this guy. So this is d eta I j m minus 2. So we are almost done. So remember that I had omega. So what I have done? I had omega m. Omega actually checked m. I wanted to replace it with something else, and then I discovered this omega m minus 1. And what else? And then I have this eta m minus 2 here. And originally I started from this here, omega m check. Okay. And so what we have done, what I am saying, that this omega m check can be replaced with the sum of these three guys. And so why? So let's make this let's say this this is delta d. Okay, so the moral of the story is that omega m check in hyper cohomology can be replaced by omega m plus omega m minus 1 plus eta m minus 2. And okay, so let me explain a little bit this one. So first of all, one has to show that d of this one is 0. And then one has to show also that omega check m minus this thing is d of something, because we want something that they represent the same de Rham cohomology, the same element in the hypercohomology. And actually all these identities, they just follow from our construction. And the basic idea of defining this map is that now we have replaced omega check with this one. Then we will repeat again with this one, and this process will go until the top elements. And in the top elements, we will see that everything becomes algebraic. Okay, maybe what can I say? For example, this why this d capital D. Remember that D was d plus delta with some minus sign. I always forget which was the minus sign. But anyway, so for example, when we take d, then this must be 0. Here we have to get 0, and this is actually the equation that we have here. So we'll get here 0 because of the equation here, and we will get 0 here exactly because of let's say the delta of this one is eta m minus 2 and omega. Eta m minus 2 we have here, and yeah, exactly this equality here will let me say the d of this one with the delta of this guy. Let me see, delta of omega ij. Let me see. When you take omega n minus 1, there are 2 indexes. Then here we have here. So you see that if you take delta of this one, this will be cancelled, and the delta of this one will be the differential of this guys, and then we will get 0 here. So maybe just I write explicitly for 0 here will follow from this one, and the 0 here will follow from this 2, and this 2 is here. Anyway, this is a kind of combinatorics that one has to sit down and do by yourself, I think. And it would I will need this kind of explicit construction of this algebraic differential form starting from C infinitive forms, because one idea of the course is to do computation. Okay, and also this this omega check represent the same element as this one is not so difficult. So this is one of the PEPs. Any question? Okay, maybe. So as I said, then one has to repeat the argument for this eta m minus 2. So this delta of this guy is 0, eta m minus. You see that the delta of this actually here is check. Delta of this guy is equal to 0, and then one will write its algebraic. No, actually, d of this guy is 0, so it is represented again by algebraic differential forms at Atiyah-Hodge theorem, and then filling all these lines in the anti-diagonal. Okay. Maybe a little bit. I explain a little bit more. The other way. Maybe okay. Let's again present the screen. Okay. So you see that at the end, we are just playing with the Atiyah-Hodge theorem in open sets in UI intersected with UG, and then in the intersection of 3 open sets, and so on. And I think it would be, if you want to follow this argument, just do one step further. Actually, here it is written the general step, this replacement with algebraic differential forms, and at the end reaching to a point. At the end, we will reach to a point that everything algebraic, and then omega check will be just omega 0 until omega m, and the last step we will not have C infinity forms, and everything will be algebraic. Okay, maybe let me a little bit talk about the the other direction, okay, so the other direction is as from a HM de Rham, this is what the I minus 1 x c to HM de Rham x infinity. Okay, so maybe this direction is a kind of is a better to analyze. So I have these elements, let's say omega 0 plus omega 1 plus omega m here. Let's say represented here, and I have to produce a differential form. And this one, I think a similar argument we did it. So d of this one, omega 0 per omega 1 plus omega m is 0. And remember that what was d? What the d was the d was up to sign. There was delta d, then delta, and so on. So in order to produce a global C infinity form, here we will just use partition of unity. So first you say here we will use that these guys, they do not have cohomology. HM x infinity differential forms, they are 0. And knowing this one again, let's start. So delta omega 0 equal to 0. So omega 0 is an algebraic object, but now I consider that C infinity form. But once I consider C infinity form, this means that omega 0 will be delta of some eta check 0. This means that there will be something down eta check 0. This eta check by delta goes to omega 0. And then I will take d of this guy. So we can replace omega with, so let's say this omega is the whole omega here, with what? With I have to replace it with omega minus d eta check 0. So remember that in hypercohomology, the things are defined well up to exact the exact object. So I can do this one. Of course, I am now out of the category of polynomials, and I am the category of a C infinity function. And when I do this one, what I will get? I will get 0 here, omega 0 equal to 0, and then omega 1, omega 2, omega m. Exactly, this combination will kill, and because of this inequality, will produce 0 here. Now my objects are no more algebraic. Here it is C infinity functions, and again the delta is equal to 0, and then I will use this, and replacing at the end I will reach to 0 0 0 0 0 omega m, and omega m it is d capital exact, it is d equal to 0, and of course it is delta is also 0, because there is no more omega m minus 1 here. So this will imply that omega m, omega is omega, let's say, this will imply that there is a global closed C infinity M form. Let's say omega in this let's say omega tilde, such that what? Such that omega tilde restricted to each ui is omega m. So remember that this notation is M forms defined in open sets ui. This is actually, then there is so remember that omega m, and in this case omega m I, and I is the index set of my covering, and then I will get this C infinity form. And yeah, okay. So well, if you had seen hypercohomology in other books, usually the emphasis is not writing explicitly the elements of the hypercohomology, but for computations we will need it. And something also I wanted to mention also about this cohomology being zero. For this one, what we use, maybe if I see if the people follow, if somebody knows what we use to prove that the cohomology of C infinity forms of our manifold is zero. Somebody can tell me? Felipe?
Sorry, can you repeat the question?
Why the cohomology of C infinity differential forms of a C infinity manifold is zero? The Czech cohomologies.
The Czech cohomologies. But no, I
okay, maybe so this is for this we use partition of unity.
Okay, yeah, makes sense.
Of unity. So the point is that the sheaf of C infinity form, they have partition of unity. You can you can take partition of unity, which is formed by C infinity function, and you multiply the elements here. And for this one, we basically use a partition of unity. Maybe I talk a little bit about this one, and then I finish the course. So partition of unity. Okay, let's. Okay, let's take our. This is a kind of this. I want to. Just a moment. Okay. X infinity. So the good point of C infinity manifolds is that they have partition of unity. So there will be, so that remember that UI is my covering. So what is the partition of unity? This will be Fi of C infinity functions in. So this will be the locally finite. In all our discussion, this will be locally finite functions in X infinity. And then what else? What else? The infinity function, and then the sum of our Fi is equal to 1 always, and the support of Fi is inside the UI. So in the C infinity context, we can always find these functions. For each UI, we can construct Fi. Remember that when I start constructing this function by this bump function, and of course, at this point where the functions becomes a constant, it's C infinity. It is no more analytic or holomorphic. Anyway, and there's some since the covering is locally finite, it can be considered is 1, and this is actually a finite sum. And okay, so once you have this, this function Si, let's call this S the sheaf. Let's say one of our sheaf, omega q x infinity. So in order to show that hm x infinity s equal to 0, then we take a relative to this covering. Maybe I have to say that this, I am now talking about proposition 2.4 of my book with Roberto. Okay, so in order to prove that, for example, the hm x infinity s equals 0, what it is, we just use partition of unity. How it works? So we take, let's say, a sigma. If you take sigma c, let me follow the notation of the book by put it here. Okay, sigma k s covering s, and then delta of this sigma equal to 0. So I have to show that this is a sigma of this sigma is a delta of something. So I have to find the we define tau c k minus 1 symmetric us, in which way tau I0 I1 ik minus 1 defined in the intersection of all these open sets. It will be just fi, and actually this sum also will make sense, sigma I0 I1 ik minus 1. So if you have a sigma which is delta exact, which is delta closed, how you find tau? You just multiply, you might, okay, first of all, tau lives in this, tau has this index I0, I1, ik minus 1. And I have to define what is this, but I have to define it through sigma. Sigma has one index more. It has, it lives in a more intersection of open set. So I just add the one index I, and then I multiply with fi, and then I take all sum over fi, and it is easy to see that delta of tau is this sigma. And so it's a kind of important remark, because what we need in order to do Sinfinity de Rham cohomology, we need just algebraic expressions and the partition of unity. And partition of unity, how we construct it with this bump function. And let me return back to this -1 map. So remember that we had this collection of algebraic, let's say 0 form, 1 form, 2 form, and -1 form. We wanted to construct the global C-infinity M form. We started to use this saying that omega 0 is a delta of something. Here we use partition of unity, and we construct this eta check 0 in the same way that I showed you. We modify it, and in the same way we do it in omega 1 and so on. So the moral of story, the story, even if you are interested in C-infinity de Rham cohomology, any element of hm de Rham x infinity can be so this is the C-infinity algebraic de Rham cohomology constructed from polynomials, the algebra, and actually, what was this? And this function. Actually, from this one we constructed this the bump function, and I forget what was this. Somebody remembers the expression of this this function, which is constant 0 here, constant 1 here, and then it jumps from 0 to 1. Alguém lembra?
Eu não lembro não a expressão dela, mas é exponencial de
e to the something
1 sobre 1 over z, 1 over I don't know.
Anyway,
something like this. Yeah.
Anyway, if you are not interested at all, let's say algebraic de Rham cohomology, but here also we have a kind of lesson for in the infinity de Rham cohomology, that really we don't need the full category for the whole set of C-infinity function. I mean, this is a very special C-infinity function, and actually it turns out that this C-infinity function together with polynomial functions are enough to construct a C-infinity de Rham cohomology. And I think this is a kind of for me a philosophical question. When you want to construct some object in mathematics, what is the minimum amount of ingredients you needed? And what I want to say that here we don't need to consider the whole C-infinity functions, just very specific amount of functions like polynomials and this exponential to 1 over something. It is enough. Anyway, so from now on, I see if I would recommend that you have a look to this isomorphism that I should try to explain. I think even myself, when I for 2 months I do not play with these notations, I also get confusion. But anyway, if it would be essential for our course to get familiar with this this playing with the Czech cohomology elements and so on. And so next lecture, so what we are going to do, so then the next lecture we will define the Hodge filtration. And Hodge filtration in HNN de Rham X. And once the Hodge filtration is defined, then we can do, I will define Hodge cycles in a more computational way and start introducing the Hodge conjecture in a way more adequate to computation. Okay, any question? Okay, so if you want to follow the course, I think it would be nice that you have a look to this isomorphism that I was trying to explain, and actually maybe just before finishing the course, I show you something. Okay, actually, this one actually my student Roberto did it, and I asked him to do this kind of heavy exercise. Your entire screen, a window. Just a moment. Let's cheer it to. Okay. Okay. So you see that even I just explained the process of defining R-1. But actually, one can give a kind of closed formula for this R-1 map. So you remember that we started with this omega 0, omega m, and we wanted to produce a C-infinity differential form. So the partition of unity relative, it is AI. And it turns out that, for example, if you make this kind of sum the i's are partition of unity, and so on. This at the end, this sum will be a C-infinity differential form, global C-infinity differential form in Xfinity in exact. So it's a kind of nice observation that even we have a closed formula for this R-1 map. And again, the proof is a kind of becoming master of playing with all these indices of open sets, of this notation that I am using, m minus m omega m I0, I1, and so let's say a k. So anyway, so just to remark that it's possible even to write down a closed formula for this map A minus 1. Okay, if there is no question, so let's the next Monday. So next Monday I will talk about the Hodge filtration. No more question? Come on. You're in, just a moment.